Okay, so next we're going to talk about probability distributions and expected value for a random variable. So in this class, we're just going to be considering discrete random variables. You might have met continuous random variables in some other classes. But for us, a probability distribution is just a table of outcomes and their corresponding probabilities. So in the section that we just covered, we had sort of boring probability distributions. They might look something like this. So we had a list of outcomes and their corresponding probabilities. And maybe let's do something like flipping a coin. So in this case, you could have X, which is your outcome, could be either heads or tails, and the corresponding probability of each would be 1/2. In other words, there's a 50-50 shot that you get a heads or a tails. Now, these probabilities in this bottom row have to add up to 1, and probabilities, as usual, cannot be negative. So all probabilities are going to be between 0 and 1 inclusive. So we're also going to be using this notation that I introduced right here. A random variable is the variable outcome of an experiment. We'll usually denote it with X, either lowercase or capital. The reason that we need a variable in the first place is because if I wanted to talk about the outcome of something like a coin flip, I don't know whether it's going to be heads or tails, but I can still reason about it by just giving it a name. So I can just say let X represent the result of a coin flip, and then I would have a corresponding probability distribution like the one that I've written here that tells me the possible values for X and their corresponding probabilities. Now in the previous section, this bottom row was pretty boring because all of the outcomes had equal likelihood. In this section, we're finally going to change that so that we can talk about outcomes that have different probabilities. So we don't necessarily need all of these to be the same number anymore. But if we were talking about something like this one, or rolling a die, then each of these in the bottom row would have the same probability or the same weight. So let's look in example 1 at just determining whether this is a valid probability distribution. Now, in the top row, we don't really have any restrictions. So X is just supposed to be listing all of the possible outcomes for an experiment. And so it's perfectly reasonable that we would have some experiment whose outcomes are 1, 3, 5, 7, 9, and 11. I don't know what the experiment is, but these are somehow the outcomes. The only thing that you really need to check to see whether a probability distribution is valid is you need to check whether this second row has all non-negative entries that add up to 1. And in this case, if you add 0.01 plus 0.02 plus and so on, if you total all of these up, what you would get is a total of 1. So this is a valid probability distribution. In other words, this does define a random variable X that has a reasonable probability distribution. In this case, it's much more likely that X will show you an 11 than it is to show you any of these other numbers. But with something like a 1% chance, you would see a 1, and with a 2% chance, you would see a 3, and so on from X's measurement. So we can do the same thing in part B. However, notice that in part B, I think if you add these up, they will still total 1. So these do have the right total. Oops. However, there's one other requirement that we need, and that's that we have to make sure that no probabilities are negative. It doesn't make sense to say that there's a negative 5% chance that X ends up being 35. So this is not a valid probability distribution. So a probability distribution is just a table that shows you all possible outcomes, so it includes the sample space, but it includes more information in that it has the second row that also tells you the probability of each outcome. And this is important whenever your outcomes are not all equally likely, like they were in the previous section. So in the previous section, it was easy to just compute probabilities because we knew that each outcome was weighted to be equally likely. But not all events are uniformly distributed in that way. So in cases like 1A here, it's possible to have a valid probability distribution where one value for your variable is severely weighted over the others. So next, let's look at example 2. It says, suppose you have a bag which contains 3 balls labeled 1 through 3. So it's like a lottery drawing. And you want to perform an experiment where you draw 1 ball at random, and then you put it back in, and then you draw a second random ball. If you let the random variable x be the sum of the number on the 2 balls, find the probability distribution of x. So for this, we might want to make a sample space for our drawing first before we make a sample space for x. So for this, we're drawing either a 1 or a 2 or a 3 as our first drawing, and then a 1, a 2, or a 3 for our second drawing. And each of these will be equally likely. So this actually will fit well into the previous set of notes. So here I would get the outcomes 1 and then a 1, drawing a 1 and then a 2, a 1 and then a 3, and so on. So these are all of the possible outcomes. But now notice that these outcomes are not describing x. These outcomes are describing the individual drawings that we get. The random variable x is supposed to stand for the sum of the number on the 2. So let's look at the possible values for x, and then we'll look at their corresponding probabilities. Because this is what our final answer will be, because we're looking for the probability distribution of x. So we're just looking for a table like this. So the top row needs to list the possible outcomes for x. So what I see is, because the table is formatted similarly to the table that we used for the sum on 2 dice, we will still have this property that the sum will be constant on diagonals. So this will be the diagonal that has a sum of 2, and then a sum of 3, and then a sum of 4, and then 5, and then 6. So the possible sums will be 2 through 6. But just like when you're talking about the result on a sum of dice, the likelihood of each of these particular sums is not going to be equal. So in this case, it's not very likely that we roll a 2 or a 6. It's much more likely that we'll roll one of these middle numbers. So there's only 1 out of 9 options that will give us a sum of 2. So that corresponds to this event up here. That's 1 out of 9 for our sample space. So the probability of getting a 2 as your sum is 1 out of 9. The probability of getting a 3 as your sum will be 2 out of 9, because that's the next diagonal here. And then the probability of getting a 4 as your total will be 3 out of 9. And then similarly for these others, you'll have a 2 out of 9 and then a 1 out of 9. So in this case, the most likely outcome of these 5 is to get a 4 as your total. And this is your probability distribution. So we just need to make a table like this that shows you all of the possible outcomes and their corresponding probabilities. The new thing is just that we have to be listing these probabilities individually, because they're not necessarily all the same anymore. So next, let's define the expected value of a random variable. So this is just sort of a weighted average. The way that I think about an expected value is that it's the expected average that you would get for the variable if you were to repeat an experiment over and over and over. So for example, if you were rolling a die, you're going to get a bunch of 1s, a bunch of 2s, 3s, 4s, 5s, and 6s. If you were to average that data set, then what you would get is a 3.5. And therefore, the expected value for a die roll, maybe I should say, is 3.5. So this is just sort of the average that you would get from a data set that was generated by your variable. So the formula goes like this. What we do is, if you want the expected value of a variable x, then you take each of the values that it can take on and you multiply them by their corresponding probabilities. So you would take the first outcome times its probability plus the second outcome times its probability, and so on, and you do that for all possible outcomes and probabilities. So let's look at example 3 here. It says, let n be the random variable defined by the number of different residences a person has lived at in the last 5 years. For simplicity, assume that everyone has lived at between 1 and 3 places in the last 5 years, and we are also given the probability function for n, which says that the probability that they've lived in one place is 70%, the probability that they've lived in 2 places is 20%, and so on. And now we need to find the expected value of n. So the way that you find the expected value of a variable is you will take the outcome for that variable, which is either 1, 2, or 3, and multiply it by the corresponding probability that that value occurs. So we have a 70% chance that they've lived in one place. So this would be the value of our variable times its probability, plus the next value of our variable times its probability, and so on. So this would be 0.7 plus 0.4 plus 0.3, which is 1.4. So an interpretation for this value is just that if you had the entire collection of people that this data was based on, and you had them write down, the number of residences that they've lived at in the last 5 years, then you would have a bunch of them writing 1s, and then some smaller proportion of them writing 2s, and then a smaller proportion than that writing 3s. If you were to actually average that data set, it would come out to 1.4. So this is the average that you would expect if you were to run this sort of experiment a bunch of different times. In other words, if you were to generate a data set using a 70% chance of showing a 1, a 20% chance of showing a 2, and a 10% chance of showing a 3. This is the average that you would expect for that data set. Okay, so we can do the same thing if we're talking about expected values for variables like this. So maybe just to give this one a name, I'll go ahead and call this x. So both of these I'm just assuming are valid probability distributions, and I want the expected value of x. Finding expected values in this form is actually a little bit easier, because here we can just take the outcome and multiply by its corresponding probability and then total all of those up. So the first outcome times its probability would look like this, plus the second outcome times its probability would look like that, and so on. So this would end up being a -2 minus 1/5 plus 0 plus 2, which is -1/5. Now remember that this is not a probability. So this is a perfectly fine answer. This is a valid answer because this is describing the expected value that you would expect from this random variable, whose values take on -10, -2, 0, and 5. So it's perfectly reasonable to end up expecting a negative average for this data set. You would get a bunch of -10s, a bunch of -2s, some 0s, some 5s, and so on, with different probabilities of each one. And therefore, the average ends up, in this case, being negative, mainly because we have a sort of a left outlier here. We have a -10 that has a 20% chance of occurring, and that's significantly further out to the negative side than the rest of our data set would be distributed. So this is the average that we get. But notice that this is not just an ordinary average of the outcomes. This is a weighted average depending on how likely each one is. So, for example, if I changed the probability distribution to make 5 much more likely, then I could turn this into a positive value, even without adjusting the possible outcomes. Just by adjusting the frequency at which they occur, I can adjust the expected value for this variable. Okay, and for this next one, I'm going to write down the expression for the expected value of x, but I'm not actually going to compute it all the way, just because these numbers are a little bit nasty. So, but I think you probably get the point that all that I'm doing is I'm taking each outcome for the variable x and multiplying by its corresponding probability, and I just total all of those up. So this would be a 2 times 0.24 plus a 4 times 0.21 plus an 8 times 0.17 plus a 16 times 0.17. So whatever this ends up being, that will be the expected value in this case. Now here, we don't know exactly what the expected value would be. I would guess that it's probably somewhere around 4, but notice that it's not going to be, for example, a negative number. It's going to be some weighted average of these values. So it'll be somewhere between 0 and 16. But where it lands between 0 and 16 depends on the relative frequency of each of those outputs. If 4 is much more likely to occur than the other outputs, then that means that this weighted average is going to be drawn toward 4. And 4 is therefore also going to be what you would expect to be the average whenever you run this experiment a lot of different times. So if you used a random variable x that had this distribution and you sampled from that distribution a bunch of different times, just like you might roll a die a bunch of different times, then this is the average that you would expect from this particular distribution. Okay, and we'll continue talking about some more examples in the next